Okay, talking about alkenes. So remember on Wednesday we talked about a little bit the structure of alkenes that are molecules which have carbon-carbon double bonds. And so in a carbon-carbon double bond you have a flat structure in terms of where the nuclei are, and the second bond is formed by a pi bond side-to-side overlap of a p orbital. And we talked a little bit about naming them. So remember some of the details of nomenclature for alkenes. You find the longest chain containing the alkene because the alkene gets priority over other carbons. Even if it's not the longest total chain of carbons in the molecule, it has to be the longest chain containing the alkene. Okay? And then you name it by replacing the ane ending with ene. Halogens have less priority than alkenes for numbering systems and directions of numbering. Alcohols, on the other hand, have a higher priority, so make sure you remember that aspect. Okay, I want to talk more details about the structure of alkenes, because it really is important to recognize that that pi bond imparts rigidity to the molecule. It shortens the distance between the carbons by having that second bond between them, that side-to-side overlap. And here's a representation of that. And again, all the nuclei, the carbons and hydrogens here are all on one plane. So they're sp2 hybridized carbons, and it's flat. The alkene structure has in it a sigma bond and a pi bond. One sigma bond, one pi bond. And when we talk about reactivity, notice the electron density here in the pi bond is located kind of in the middle of that. Could go to either end of a carbon-carbon double bond if it's not polarized. The electron density in a double bond can be shifted one direction or another. For example, if one of these atoms is not a carbon but an oxygen, if you have a CO double bond, guess where the electron density in that pi bond is shifted more towards? The oxygen. It's a more electronegative atom, right? So in that case, it's a polarized double bond. And that's important for reactivity. The bond strength. We were talking a little bit about this at the end of class on Wednesday. If you look at the energy which would be required to break both of the bonds homolytically, putting one electron from each bond on each carbon. By the way, that's high energy and hard to do, like this. But if you compare that bond dissociation energy, the enthalpy of the double bond versus the enthalpy of a carbon-carbon single bond, you observe that the double bond isn't double the energy of a single bond. It's something less than double the energy. So if you were to double the energy of a single bond, you'd be at about 750 kilojoules per mole for the double bond if it were just doubled. In fact, the single bond, or the sigma bond, is stronger, has more energy, bond energy, than the pi bond. And that's due to the fact, in principle and in general, when you have end-to-end overlap, that's the optimal way in which orbitals can overlap. So a sigma bond, an end-to-end orbital overlap, is the strongest. A side-to-side pi bond, or side-to-side overlap, is a little bit weaker. So if you factor out 375 kilojoules per mole here, what you see is that that's about, what, 355 kilojoules just for the pi bond. Okay? So when we talk about reactions in the future, the double bond is going to be weaker than the sigma bonds, and so that's what we think about first when we think about how the molecule reacts. Which bonds are going to break first? The weakest ones, right? So that's important to recognize as well, the strength of the bond. But the other aspect of a pi bond is this. That is, when you have this side-to-side overlap, it's oriented in one direction. Okay? If you rotate the carbon in a double bond relative to the other carbon in the double bond, what would happen is you would break the overlap between the p orbitals. So here, in order for that side-to-side overlap and bonding to exist in this pi bond, it has to be aligned in the same direction. Okay? If it's this case, and this is looking down, sort of looking down that CC bond, they have to be overlapping. If you rotate, you'll see that there can be no overlap now between the front carbon and the back carbon, right? So the molecule is fixed, it's rigid in terms of the pi bond. And that has consequences now when we think about the other groups which are attached to those carbons, okay? And I will say it's not that this bond can't rotate. It could give it enough energy. It's just a high energy process. You have to actually break the bond and reform it if you rotate around. Anything can be broken given enough energy. But it is high energy, and so certainly at room temperature, alkenes are stable and the carbons relative to each other do not rotate. What other kinds of molecules have we seen that have rigid structures that don't allow rotation? Cycloalkanes, right? Cycloalkanes, by virtue of the fact that they're tied in a ring, can only move so much depending on their size, right? The size of the ring. So it can't completely rotate around. Otherwise, you'd have to break a carbon-carbon bond in order to rotate completely around. Well, it's the same principle here and the same consequences because of this, alkenes can exist if you have different substitution on it as stereoisomers. Okay? Molecules which have all the same bonds and atoms, all the same kind of bonds and atoms, but are just arranged differently in 3 dimensions. We haven't moved the positions of any atoms or the bonding between any atoms. So we saw that with rings because we can have groups on the same side of the ring or groups that are on opposite sides of a ring. And they're fixed there because there's no free rotation completely around the bonds in a ring. It's true here also. So think about the double bond structure. Okay, think about the double bond structure. And all of the bonds are 120 degrees apart roughly, right? And that's fine. If all of the groups, all the substituents on there are all the same, it doesn't matter. Or if one side of the double bond has 2 of the same groups, there's no relative position to the other end of the double bond. But if they're different, it's a different story. So let's just take a look. If you look at the isomers of butene, okay, there are 4 different isomers of butene. One of them is 1-butene, where the double bond is between carbon 1 and carbon 2. Okay? And although these bonds, the 2 hydrogens here, the hydrogen here, and this group are all fixed in space, and there's no rotation between the carbon-carbon double bond, if you were to exchange, these CH2, CH3 group here and make this hydrogen and put the CH2, CH3 down here, would that be a different molecule? No, because if it's on the top, it's on the same side. If you look at one end of the double bond versus the other, it's on the same side as a hydrogen. And if you put the CH3 down here, it's also on the same side as a hydrogen. Okay, because these 2 groups on the left side are identical, it means it doesn't really matter where you put the groups on the other side. They have the same relative relationships. Okay? Another isomer is this one here, 2-methyl propene. Okay, so I've simply taken one of the carbons off the end of the chain and attached it here. So again, what we have is a double bond. That's the rigid part, the CC double bond. And here we have a hydrogen on the same end as a CH3. And this is also a hydrogen. Okay? As a matter of fact, both of these groups on the left are identical, and both of the groups on the right are identical. It doesn't really matter how you switch them around on each side. Okay? You all have the same molecule. But once you now start having situations where you have different groups on the left side of the double bond and different groups on the right side of the double bond, now you have a situation where if you switch them from the top to the bottom, as I've drawn here, you get a different stereoisomer because it's fixed in space. So trans 2-butene, this trans we're familiar with from the groups on a ring, right? Trans meaning opposite sides. So if you look at the double bond where you can't rotate because of the pi bond, and you have a hydrogen on top and a different group now on the bottom in the left. And the same thing is true on the right. You have a different group on the top here than you do on the bottom. So what you have then is a situation where if you position the groups the way I've drawn it here, you have similar groups. Here's a hydrogen on opposite sides of the ring. That's what we would refer to as a trans orientation. Okay, compare that to the same molecule on the right. We haven't moved any groups around in terms of breaking up where it's attached and moving it to a different attachment. We've only switched the position in 3 dimensions. This CH3 group is still attached to that carbon. Okay? But I've just drawn it now on the bottom side. So we use the term cis to refer to the double bond where 2 of the same groups are on the same side. So you can look at this either way. In this case, the 2 hydrogens are on the same side as each other from one left to right, or the 2 CH3 groups are on the same side from left to right. Okay? We see these kinds of stereoisomers all over the place in double bond chemistry. For example, if I just draw something like this, how would you name that molecule? Using, in addition to the name of the molecule, cis and trans designation for the orientations of the groups on the double bond. How many carbons is it? 7. So it's a heptene, right? Heptene, and the double bond starts at which carbon number? 2. So it's a 2-heptene, but, and I point this out because we don't always draw the hydrogens. It's important to recognize where those hydrogens are on the double bond. So remember, even when I draw these line structures, we're assuming that the double bond is flat, planar, and that the groups are 120 degrees. So we would put a hydrogen here pointed up and a hydrogen here pointed down. Since we don't draw them out, all the hydrogens on line structures, it's important to recognize that. So if you take a look then at the double bond here and divide it in half, on the left side there are 2 different groups, and on the right side there are 2 different groups. So if we compare then the same group on each side, here we have a hydrogen and here we have a hydrogen, they are on opposite sides, so they would be trans. So this would be, the name of this would be trans 2-heptene. I could draw the cis 2-heptene. In a line structure, I would draw it, let me see, is there room here? I would probably draw it like this. Was it 1, 2, 3, 4, 5, 6, 7? That would be cis 2-heptene. Notice the way I've drawn the double bond, and the hydrogens that I haven't written would be pointed here and here. Okay, on the same side of the double bond. Okay.
So
yes.
So if I just draw it like the bottom one and use it just put both the hydrogen in the same direction, doesn't matter.
Well, from the way I've drawn it here, from the way I've drawn it here, to keep the 120 degree bond angles, right? Even if I didn't draw it, if you drew it like this, that means that this group and this group are on opposite sides. Okay? Because you have to assume that the hydrogen is pointed down here and pointed up here. So be really careful about that. I see this mistake commonly made a lot of times. So recognize that that double bond is flat and you have 120 degree bond angles.
So this one doesn't have 120 degrees?
They do, sure. It's the same. This is 120 degrees, this is 120 degrees, and this is 120 degrees. It is the same. But notice where I've drawn the carbons on the same side of the double bond versus on opposite sides of the double bond. Okay? And you can orient these molecules however way you want, but you have to consider that, like if I draw this. Okay, is that a trans double bond or a cis double bond? Trans, right. Notice the carbon here and the carbon here on opposite sides. And the hydrogens that aren't written are here and here. I oriented the molecule in a different way, but the double bond still has the carbons and hydrogens on opposite sides. Okay, so be a little careful about that. Any other questions on this? Double bond geometry is actually critically important for all of you because without double bond stereoisomers and the ability actually to switch from one to the other, none of you would be able to see. As a matter of fact, when you eat your carrots, you're ingesting beta carotene, which is this. Actually, I think I have a typo in that structure. There may be one more carbon missing here. There should be another double bond somewhere. Anyway, beta carotene has this molecule which has a lot of double bonds in it. These bonds are all conjugated. I use this term to refer to pi systems which alternate. Recognize that a double bond is a pi bond where you have overlapping p orbitals. So if you look at this molecule, there's a p orbital on every single carbon where they're alternating double single bonds, right? Etc. What do you think happens to all the electrons that are involved in those double bonds? Is it there, and there, and there? No, it's spread out. Okay? They're all spread out along the whole pi system that's connected with a p orbital on every carbon. Because of that, they're easier to break at lower energy and actually at the energy of visible light. What happens when you eat beta carotene is it's metabolized in your body to vitamin A, which has been metabolized into this molecule which we call retinal. Notice all the double bonds here are trans double bonds. In particular, this one I've highlighted in blue. Notice that's a trans double bond there. This is incorporated in your retinas. It's buried inside of a protein in your retina. And when your retina absorbs light, that photon of light has just the right energy to momentarily break that double bond and allow it to rotate and then reform. And so that double bond converts from a trans double bond to a cis double bond. Okay, and that changes the shape of the molecule. When that molecule changes shape, it changes the shape of the protein, and that sets up a signal then through your optic nerve to your brain that you have absorbed a photon of light, and that's how we see. So double bond geometry is really important for biology. There's a problem, though, when we use the cis and trans designation, because it doesn't consider all the different possibilities that you could have for groups. Because when we use cis and trans, what we're talking about is two of the same groups being on the same side or opposite side. So you have two hydrogens on the same side, one on the left, one on the right, or two CH3 groups on the same side or the opposite sides. We can clearly designate what is cis to each other and what is trans to each other. Okay, but what if you have a molecule like this? We have a double bond, ethene, where we have a hydrogen and a chlorine on one side, a fluorine and a bromine on the other side. And without changing the positions from moving a group from one carbon to another, we could switch their orientations on one side or the other, right? So for example, if I just switch the positions of bromine and fluorine on the same carbon, I have a stereoisomer. Okay, but when you use a designation of cis or trans, what groups are you talking about being on the same side or opposite sides? Huh? Which?
Carbon?
Well, no, we're not talking about the carbons. We're talking about hydrogen. So we have to consider the hydrogen and chlorine on the left side. So if I couldn't use cis here, right? Because chlorine would be cis to bromine and hydrogen would be cis to fluorine. So there are no two of the same groups on the same side. So when you use cis, what are you talking about? It doesn't make sense, right? It's not clear. It's ambiguous. So we have to have something else. And again, we have to look at the left side versus the right side. There's two different groups on the left and two different groups on the right. So for this molecule, what we do is we refer to this as the Z on the left, and I'll explain this in a minute, or the E molecule on the right. So it's analogous to, Z is analogous to cis, and E is analogous to trans, because these come from German words, entgegen meaning opposite, and zusammen meaning together, or on the same side. I kind of remember that cis, Z, it has kind of that same sound, right? But what we have to know is what are we talking about? What's on the same side relative to the other side, or opposite sides? And for this we have a system to designate the priority. So in this case, it's the highest priority group on the left side of the double bond versus the right side of the double bond that we're comparing. Not necessarily the same kind of group, but the highest priority. So since groups could be all kinds of different things, we need to have a systematic way to designate priorities of groups. What gets highest priority, what gets lower priority. And so there's this set of rules which are referred to as the Kahn-Ewald-Prelog rules, which designate how we distinguish priorities. And the first thing to consider is the atom that's directly attached to the carbon. We rank it according to the atomic number of that atom. So in this case, on the left side of the left side of the double bond, we have a hydrogen and we have a chlorine. Okay, which of those has the higher atomic number? Chlorine. So the chlorine is the higher priority group. Okay, on the right side we have a fluorine and a bromine. Which is the higher atomic number? Bromine. This is why I would name this as the Z isomer, because the highest priority groups are on the same side of the double bond. Okay, and if I switch that around as I've done on the right here, the highest priority group, chlorine, and the highest priority group, bromine, are now on opposite sides. Okay? So the first thing you do is look at the atom directly attached to the carbon and say which of those groups on the left has the highest priority, which of the group on the right has high priority, and then how are they related from left to right. Okay, it gets a little more complicated when you have organic groups, alkyl groups, especially if you have the same atom. So if you take a look at this, this molecule, if you look on the left side of the ring, I keep saying ring, on the left side of the double bond, okay, again, we're comparing this. It's clearly you can distinguish the highest priority group, right? You have the chlorine versus hydrogen. Chlorine has the higher atomic number. But if you go to the right side, the ethyl group versus the methyl group. The ethyl group gets the higher priority, but the question is why? Okay? If you look at the atom directly attached, you have a carbon versus a carbon. Those are the same. They have those atoms have the same atomic number. So you can't distinguish a priority of the whole group from that. So the way you do that then is to go to the next atom out. I consider this like layers of the onion. You go to the next layer out of atoms attached to those, and see if you can find a distinction. And one way I like to do it is to draw this out sort of like a tree diagram. So if we look at this CH3 group on the top, okay, directly attached to the carbon we have a carbon, I'm sorry, directly attached to the double bond carbon we have a carbon on the top group, right? And the bottom group we also have a carbon. That's that first layer of the onion, if you will. We can't make a distinction. So we see what's then attached to that atom. So on the top, we have what attached? 3 hydrogens. Hydrogen, hydrogen, and hydrogen. That's the next layer out. And on the bottom, we have a hydrogen, and then another carbon. There now we can make a distinction. Okay? If we can't tell the difference in priority from this layer, we can tell the difference in priority from this layer, because now we have this one being a higher atomic number in that layer, or that layer out that we've done. So what you need to do is you need to systematically go from the first atom connected and see if there's a difference, then go to the next atoms that are connected, see if there's a difference. If you can't make a difference there, you need to go even further. Once you make a difference at one of those layers, you don't go any further. Okay, that distinguishes your priority. So that's why, in this case, the ethyl group gets the higher priority over the methyl group. Does that make sense? Question?
What would you name that molecule?
How would I name that molecule? Let's see, let me clear this out for you. I would name this molecule, let's see, it's the longest chain would be 1, 2, 3, 4. And there's a methyl group on 2 and a chlorine on 1. So I would call this E instead of trans. E1 chloro 2 methyl 1 butene. 1 referring to the position of the double bond. Okay, so E, that designates the stereochemistry of the groups. 1 chloro, 2 methyl, 1 butene. Good question. Any other questions on that one? Let me show you another one. Okay, take a look at this one. Okay, this happens to be a Z alkene. A Z alkene. Because the 2 highest priority groups are on the same side of the double bond. Again, the left side here is pretty easy. I've made it simple in this example. Hydrogen versus chlorine. The chlorine will have the higher priority. But in this case, it's the smaller carbon group which gets the higher priority, not the larger carbon group. Even though there are 4 carbons down here, and it's a bigger in size molecule, it doesn't matter. By our systematic rules, we go out 1 layer at a time until we can make a difference or a distinction. So again, if you look here, it's carbon and carbon at the first level. You go out to the next level, this carbon is attached to a hydrogen, hydrogen, and oxygen. And this carbon is attached to a hydrogen, hydrogen, and carbon. Here we have now an atom which has a higher atomic number than any of them. And so that makes the top group have higher priority. Okay, it doesn't matter what else is out there. We've made the distinction at that second level, and that's where the EZ priority designation occurs. Even if I had something out here, let's say I take this, instead of a CH3, I had, I don't know, a CH2 iodine. Iodine might, oops, sorry, this is all marked up. Let's say I put a big heavy atom out there. This would have a higher atomic number than anything else, but it doesn't matter. We made the distinction earlier than that. It doesn't matter what else is left out there, or the EZ priorities. That's, yes, question?
What if there's 2 carbons connected to the original carbon like
if there are 2 carbons connected, no. It's atomic number. It doesn't matter how many of a lower atomic number there is. It goes by atomic number. Good question. That's also an important point.
Now,
atomic number. How about this one? This is a little different than the one you asked. Is this an E alkene or a Z alkene? I had someone say E. How many agree with E? How many think it's Z? Okay, let's take a look at this. The left side's pretty easy, right? I haven't changed that. First layer. Here we have a carbon on the top and we have a carbon on the bottom. Right? No distinction. This carbon is attached to 2 hydrogens and 1 carbon. Okay, and this carbon is attached to 1 hydrogen and 2 carbons. Now we have a difference. This one and this one cancels. This one and this one cancels, but now we have hydrogen versus carbon. We have one more, and it's not comparing the oxygen at all because we haven't got out to that level. Doesn't matter that this oxygen is here. This carbon at that level earlier in our tree tells us that that should get the higher priority group. So that's an E double bond. So all of you who said E, that's right. Okay?
How would you name that group? The top right group.
The top right group? Oh, so by the way, the priority doesn't mean it's the longest chain for the name. The priority is just for designating EZ. So the molecule, remember OH groups for naming, not for assigning priority necessarily. OH groups for naming get preference. So this molecule's parent chain would be that, and we number from the alcohol. So then we would name this as the substituent. So please don't confuse how we designate priority one layer at a time for EZ versus how we designate the longest chain or name.
If you go back to the other one, it would be the longest chain would be the 3 because we would start with that.
That would be this one. Oh, sorry. The next one, right? So if we go with this one, the longest chain containing the OH gets priority for naming and chain. So this, actually, if you were to name this, it would be a propene. Even though that's a big carbon group there, the name would be with the alcohol. And it gets a little confusing, I know. So be really careful not to mix those things up. Okay, any other questions on this? What else do I have here? Okay, now this is another complicating factor. How do you designate priorities when you have pi bonds in the groups that you're looking at? Okay, so in this case, we have an alkene where we have an atomic number difference on the left side. On the right side, it's a little more complicated. Okay? The way we treat multiple bonds for designating priorities for EZ is to imagine the double bond are additional bonds to the atoms they're connected to. So for example, this double bond on the top, we think about it as if so imagine, if you will, breaking that double bond, putting one bond here, and putting another bond here, and if you swing the bond up this way, it was attached to a CH2. That's what I've drawn. In blue, those are imaginary atoms, not real atoms. And if I swing the bond up this way, it's a CH group which swung up, and so that's what I imagine is over there. So we have to do this when we have double bonds because we consider that double bond to be the same number of bonds to the kind of atom it's connected to, in this case carbon. So this is how you envision this group when you're trying to assign the layers and priorities. Okay? So if I look at this group here, that's designated down here. This group now, we would think about like this. So the first level, carbon versus carbon, there's no distinction. The second layer out, carbon, hydrogen, carbon, and carbon, imaginary though, but that's how we consider it, hydrogen, carbon. No distinction, right? In this case, we go a third layer out, and that's why having these imaginary atoms is important. Here it's all hydrogens. Here we have one carbon, imaginary though it is, that distinguishes our difference in priorities. Okay? Question on that? It would be the same thing if we had a double bond. Instead of this group, we had a double bond to an oxygen. We would consider that group, if we were to think about what that would be, the imaginary group would be a CH and bonded to an O, and if I swung this up to the left, we'd have a bond to an oxygen, and if I swung this bond up to the right, we'd have a bond to a carbon. So that's how we would imagine that group, a carbon or a CH, right? So multiple bonds to any kinds of atoms, we just think about breaking it and putting those imaginary atoms in when we try to think about these just differences in the priority groups. All right? I wouldn't throw things that are too complicated at you because it could get really, really complicated. But those are the rules. Those are the process you would follow. And if you really are careful about being consistent and looking one layer at a time carefully, you'll always be okay doing this in assigning a priority. Okay, any questions on commingled Prelog priority rules? These will be important later for other aspects of stereochemistry and determining priorities of groups as well, not just for easy on double bonds. So the system for assigning priorities will come back even later when we talk about other things. Okay, let's take a look at some of the properties of double bonds. This is a chart just showing the energy differences of the amount of energy released when you burn these isomers of butene. Remember, the heat of combustion is the energy we get out when we burn a hydrocarbon all the way to CO2 and water. And if they're just constitutional isomers or even stereoisomers, the energy differences are related in how much energy we get out when we burn it all. Okay, that tells us something about how the way things are connected or oriented in 3 dimensions affects the overall energy of the molecule. So the more energy you get out, it means the molecule was less stable or higher in energy. And you see some interesting trends here. If you have one butene, this molecule on the left, one butene, it's the highest energy molecule. Okay? And if we have the isomer, which is 2-methylpropene, it's the lowest energy molecule. So we get less energy out when we burn it. So it's more stable, right? It's more stable. Notice, though, if we have 2-butene, either the cis isomer or the trans isomer, it's somewhere in between. But even those two are slightly different in energy. Okay, so there are aspects of these molecules which affect the overall stability of a double bond. Okay, one of the things is that the more substituted a double bond is, the more stable it is. So that's one aspect, and that's for the exact same reasons that a carbocation is more stable with more substitution on it, and a free radical is more stable with more substitution on it. It has to do with hyperconjugation, and we're talking about the same thing. In a carbocation or in a free radical, you're talking about a p orbital on that carbon. When we have a pi bond, a double bond, we have p orbitals on those carbons. And so hyperconjugation and being able to, in some sense, spread out electron density helps to stabilize it. So the more substituted it is, the more stable it is. Okay? As a matter of fact, I don't have it on here because it's not, it adds more carbons, so it wouldn't be a good comparison here. But if you had the tetra substituted, you have a carbon substituted on every single atom, every single carbon of the double bond, 4 groups on it here, that would be even more stable and lower in energy. Another thing I want to point out, if you look at the 2 molecules which are 2-butene, either in the cis or the trans orientation, or by the way, I could call that Z and E. I should mention also, Z and E, you have to use Z and E when all 4 groups are different on the double bond. If you have 2 groups which are the same, 2 hydrogens or 2 CH3 groups here, you could use cis and trans, but you could also use E and Z. The priority rules work just as well. You see sometimes that interchanged. Okay, so I could call that E2-butene and Z2-butene also. But they are different in energy. The trans isomer or the E isomer is a little bit lower in energy. Why do you think that would be? Yes?
Less van der Waals strength.
Less van der Waals, right. It has less steric interactions because when you put groups on the same side, like in the cis bond, just like we saw in some ring molecules, they come close together and then you have steric interactions. Okay, these are further apart. So that will be lower in energy. That is part of that difference in energy. Another part has to do with how those groups polarize a double bond. So when we polarize things, they tend to be higher in energy when we separate charge. One thing to recognize is that, just like when we talked about stability of carbocations, alkyl groups are electron donating groups. So they're pushing electrons towards the carbocation or towards a double bond. And you can see here that the dipole moment for the molecule, for all of these, somewhere between 0.3 and 0.5. It's not big, but for 3 of these molecules, there's a dipole moment. But for this trans 2-butene, the dipole moment is 0, meaning overall, if you sum up all the individual bond dipoles in the directions, they cancel out here. Okay, it's completely nonpolar. Why would that be? Well, alkyl groups are very slightly electron donating, electron pushing. So if you think about 1-butene here on the left, we have an alkyl group which is pushing electron density. So overall, the molecule will be slightly polarized. All right. If you have cis 2-butene, you have along the direction of the bond here, you have some electron density pushing this way. And here you have electron density pushing this way. So overall, the molecule will have a slight overall dipole moment in that direction, right? Because if you add up all the dipoles, these 2 would add up and give a slight dipole in that direction. Same thing here all the way on the right. We have an electron donating group here, an electron donating group here. Overall, the molecule is going to have a slight dipole in that direction. Okay? And the double bond, it actually gets polarized a little bit. So that makes sense that you would have a small amount of polarity in the molecule. But for this trans isomer, notice that they are counteracting each other along the same direction. So if you look at this bond and this bond as the 2 major contributors, right, they're equal and opposite. So they would cancel overall. Overall, the molecule has no dipole, and that's why the dipole moment is 0. Question?
Does it mean that the trans isomer is less reactive than all of them?
The trans isomer, if it's lower in energy, it's more stable, and yes, it's less reactive. That's absolutely true. And there's less polarization, and so you would, for a lot of reasons, it would be less reactive. There was something else I was just going to mention. Oh, if it's something besides alkyl groups, you also have polarity effects on the double bond. So imagine if this, instead of a CH3 group here, imagine it was a chlorine. Okay, what would happen to the dipoles in that case? This one is slightly electron donating, the carbon, right, of the methyl group. What is a chlorine? The electronegativity of chlorine versus carbon? It's large, right? Large difference. Chlorine is much more electronegative than carbon. It's an electron withdrawing group, and a pretty strong one. So overall, this molecule now is going to have a dipole in that direction. And not only that, since this is pushing into the double bond and this is pulling from the double bond, let me just erase this, you're probably going to have more positive charge here, or actually that's not right. The electron density in here will be shifted more this way, probably towards the electron withdrawing group. Okay, it's going to be pulled, the double bond is going to be pulled towards the chlorine. So those things do affect the electron density in the double bond as well. Okay, electron withdrawing, electronegative effects, inductive effects do affect the overall property of the alkene. Okay. So in general, as I mentioned, the more substituted the double bond, the more stable it is. And again, it's because of this aspect that we have p orbitals, and for a more technical reason, it has to do with the antibonding orbital. If we look at the molecular orbitals for a pi bond, that's where electron density is being donated into from adjacent bonds. So this is, again, what we refer to as hyperconjugation. That's one thing, and the electron donating ability of the carbon. So hyperconjugation, if you have more of that, that's an additive effect. The pi bond becomes more stable, lower in energy, harder to break if you have more and more substitution. Okay, more and more alkyl substitution. Okay, the substituent effects, as we just talked about, you can have different types of steric interactions, as shown here when we have two butene, cis and trans. As a matter of fact, if you just take either cis or trans 2-butene, and you heat it up with a little bit of acid catalyst, you see it will isomerize from one to the other. We'll get a double bond rotation. That occurs, by the way, by protonating. So the double bond will get protonated. We'll form a carbocation on one end and put the hydrogen on the other. Okay. We get an intermediate. We've seen these kinds of intermediates before, right? Well, now, if we break the double bond in this way, we can allow the CC bond to rotate. And deprotonation, or loss of that hydrogen, the electrons flow back down, and this comes off, will reform a double bond. So you could break the double bond, form an intermediate carbocation. The single bond now between the carbons can rotate, and then you can reform the double bond by loss of the proton, and reform the double bond. But in the process, you could switch those groups. And when you do this experiment, what you see is that the cis double bond, you get about 24% when this is in equilibrium versus 76%. So it's about a 3-to-1 ratio. You get more of the more stable molecule. Okay. So that's the thermodynamically more stable molecule when you have this equilibrium happening. And it clearly shows that that steric interaction is important for the stability. If these groups are even larger, it's even worse. If these were, instead of a methyl, if these were both tertiary butyl groups, you would have none of the cis isomer and almost exclusively the trans isomer. Because then you have even more steric properties. Okay, on Monday we're going to talk about how we actually synthesize double bonds, how we form double bonds through elimination reactions. So we'll talk about the preparation and details of the mechanism for that next week.